Hey everyone, it's 1 o'clock, so we're going to go ahead and get ourselves started. I'd like to welcome you to another DesignSafe webinar, the one for October. So we do these webinars frequently throughout the semester as a way of bringing the community together, showing what's new within DesignSafe, and also providing a little bit of input on where DesignSafe came from and what our goals are. I would also like to welcome any suggestions for future webinars. If you have one, please feel free to shoot us a ticket or contact us through the Slack channel. And there'll be more ways. I'll give you guys a little slide on all the different means of communication with the DesignSafe team. So today we're going to be talking soon here. I'm going to be introducing Barbara Simpson from the Oregon State University. She's going to be chatting about leveraging Python, Jupyter Notebooks, and DesignSafe and the SimCenter educational tools in the classroom, which is important to a lot of us since a lot of us do teach as well as do research. DesignSafe has a lot of features that can be useful in the classroom. And this is one of the first of our webinars to actually discuss that in particular. So let me introduce myself. I'm Charlie Day. I'm the Director of Training and Professional Development here at the Texas Advanced Computing Center. This is where DesignSafe is actually hosted on our machines, and the infrastructure was built using our systems. So a little bit about DesignSafe. So DesignSafe, for those of you who are unfamiliar or new to our cyber infrastructure, DesignSafe is a CI that our goal is for it to become an integral and dynamic part of your research. We have a bunch of cloud-based tools that support analysis, visualization, and integrating different data types into one big umbrella that can enhance your research. The idea is we want to be able to unlock the power of what we call big data. Big data has a lot, it's kind of a big buzzword, so it goes everywhere. But essentially the idea is data is too large to be able to store on your laptop, so you can store it on the cloud resource. But once it's on a cloud resource, you want to be able to have the tools necessary to do the analysis work on that data. That's where DesignSafe comes into play. You're holding your structural analysis data, for example, on DesignSafe, plus the tools are there, and the computing resources are there, and the community is there to help support your research work. And that's the idea, is we want to be able to support the end-to-end research workflow. That is from the conception to the discovery, to the presentation, to the publication. And of course, the DesignSafe staff is there to help you along the way. And of course, we are part of NHERI, and so one of our goals is to enhance and amplify all the capabilities of all the other NHERI components under one umbrella. So DesignSafe is broken up into a couple different pieces. So if you're unfamiliar with these, we have the simulation research, the experimental research, and then the rapid research. All of that individual information, all of that data that these different sections produce are all stored on the data depot. And then through the data depot, we give you, or through DesignSafe, we give you the discovery workspace that allows you to do your analysis work, create new data sets, create scripts, create Python scripts and R scripts, and run Matlab scripts to be able to analyze that data. Plus, there's a bunch of other applications that are there to help you with your research work as well. And then once your research work is complete, or once your project, once you had a good place in your project to publicize, you can then curate and publish your data, not just your paper, but also the data sets that your research created. And so when other people use your data set for their own research, they can then link and essentially give you the reference to, and give you the citations to your data sets for their research. So we'll talk a little bit about the data curation philosophy. One of our goals was, when we created DesignSafe, we wanted to allow users to easily store, share, and document and publish their data through the life cycle of the entire project. From beginning, when you're just analyzing what your data structure may look like, to the end when you have terabytes and terabytes of data sitting there and being analyzed. And because of this, because we understand that it's not a one-size-fits-all category, especially with the natural hazards researchers. Our data model had to be flexible. It has to have a process, but even being flexible means there still has to be a process to curate the data so it's understandable. So to do that, we actually created some a hierarchy, so to speak, or a design tree of how you can categorize your data. So we give you these data models that you're allowed to use and build. These data models are designed by you. How do you want your data to look? How do you want your data to link to other data? And at DesignSafe, we also have a expert data curator on staff at TAC. That is Dr. Maria Esteva. And Maria is fantastic to work with. And to help you curate your data, she holds what we call virtual office hours on Zoom at that particular Zoom link. It's also available on DesignSafe's website if you can't remember the link that quickly. And she will help you look at your data set, understand what the story your data is trying to tell, and then be able to show you how to properly curate the data so that story is told properly. It's actually a really simple process. You define your category tree of how you want your data to be laid out. Then you assign the categories to different files, different data files that you have sitting inside the data depot. And then it's a question of publishing the project and publishing the files by just saying, hey, I'm ready to publish. And once it gets published, a DOI gets assigned to that data set and to that project, and then other people may then cite that data set. All right. So getting your data into DesignSafe, there's multiple techniques. You can use the data depot directly by uploading through the Jupyter notebook or uploading directly through the data depot. You can also load your data into box.com, Dropbox, or Google Drive, and then copy it into DesignSafe. There's also a very, very quick manner, but it takes a little bit of understanding and tweaking to get it to work right. It's called Globus. Globus allows for a large number of files and large number of folders and large sized files. And then, of course, for those of us who really like getting dirty with the system, we give you the command line interface. You can actually type your commands in directly using rsync and SCP. For more information on transferring data, we have provided a data transfer guide, and we do have a specific guide on using Globus. All right, so we want you to make your data count. So we really do like you to be able to use DesignSafe to hold your data set, to store your data set. It's a permanent location. You get a DOI, not just a URL to the location, but an actual citable DOI. And then, of course, we can formally cite your data in a reference list for other papers in your own paper and for other people in the DesignSafe community. All right, so with that, I would like to introduce Dr. Simpson. So Barbara Simpson, she has teaching interests in seismic design of steel frame structures, plastic design, and earthquake engineering and structural dynamics. She has actually started using DesignSafe in her classroom, and she is leveraging Python, Jupyter notebooks, DesignSafe itself, and the SimCenter educational tools to basically enhance the classroom experience with her students. So without further ado, let me introduce Barbara. Hey, Barbara, I'm going to stop sharing my screen, and then you can start sharing yours. And afterwards, I'll give you a few closing remarks.
Okay.
So much, Barbara. Really appreciate your time, and looking forward to your presentation.
Okay, so let's see if I can share my screen. This is always the hardest part. Okay, I'm assuming that this is being shared. Is it on the screen?
Yes, it is.
Okay, fantastic. So this is kind of an interesting presentation. I think the majority of us have talked a lot about our research and maybe less about our teaching or the potential things we could be doing with our teaching. And so in particular, I'm going to be talking about Python, Jupyter notebooks, how those are being leveraged through the DesignSafe user portal, and also the SimCenter educational tools, which are available and can supplement our teaching and just make everything a little bit easier when it comes to having some sort of graphical user interface for our students and them understanding the material that we're trying to educate them on in the classroom. So just to give a general outline of what I'm going to go over today. So I'll introduce this sort of Python and Jupyter. I know a lot of us were educated or possibly still being educated in the age of Matlab, but I think a lot of us also see the writing on the wall, and we're starting to take Python more and more seriously as an open source programming language. I'll go through some examples of what we're trying to do at Oregon State University, mainly with Python and Jupyter notebooks, as well as the SimCenter educational tools. And then finally, I'll present some of the educational apps that we've been using in the classroom rather successfully, I would say. So let's just start out with this Python and Jupyter. So I think many of you might be wondering why Python? You know, why not Matlab? And I have a couple sort of philosophical things that I like to mention when it comes to Python. I think Python's actually pretty great for beginners. So if you're a beginner user and you've never really programmed before, it has a great syntax that's fairly easy to understand. I also think, given that Matlab also has a syntax that's pretty easy to understand, Python's pretty good for learning other lower level languages. So I have a philosophy that when using Matlab, you can make things work that maybe shouldn't work. And Python sort of takes some of those things away. So for example, in Matlab, you can have dynamic arrays that just grow. They just you can add things to them and they just grow all by themselves. You know, you have to actually take a little bit more in mind about initialization of your variables, maybe what variable types you're using with Python. And I think just as far as the beginner user, it actually makes you a better programmer if you're extending or really using any programming language. And so it makes it easier to understand languages like C++, for example. It's pretty simple and consistent. It also has a number of third-party libraries, almost an infinite number online. So for example, if you want to do something, say with machine learning, there's a very large machine learning community, and you could download one of those libraries and incorporate them directly into whatever programming you're trying to do or whatever solution strategy you're trying to use. So there's a variety of third-party libraries that are all open source. And the fact that it's open source and free makes it it has a definite advantage over Matlab. So Matlab might be free to students, but when a lot of our students are exiting academia and moving into the workplace, we're seeing that a lot of the high-level companies are more and more moving to these open source sort of software. One of them being programming more in Python, whereas before Matlab was more of the status quo. I'd like to point out that it's easy to learn for small scripts, but it's actually very scalable for large systems. So as you get to program more and more complicated things, say working with OpenSees, the Python programming language is very scalable in that respect. And I think one of the more important ones is that it's been thoroughly embraced by the machine learning and data analytics communities. And there's been growing population of the use of Python in engineering. And so I think, like I said previously, a lot of us are seeing the writing on the wall. I think more and more, as the Python community, which is already quite extensive, grows even larger, I think this is a programming language that we want to be teaching our students and want to have our students leverage as an open source programming language with all the third parties, libraries, and support that comes with that. And so I just kind of wanted to say, so why not Matlab? So I'm a numbers person. So basically, and I didn't come up with this, which makes me even love it even more. So let's just put a couple of numbers. So where higher numbers denotes like a sort of, this is great, and the lower number means this is not so great. And so if you look at Python comparison to Matlab, number one, it's open source. Number two, it's free. Both Matlab and Python have very, very powerful numerical functions, and they are easy, and they're great for scientific applications. But the thing that I like about Python is that it's extremely general. And so things that might only work in Matlab, with Python, you can actually generalize to quite a number of other problems and other programming languages as well. It's easy to extend It's fairly small in size. And I think that the one downside to using Python versus Matlab would be the access to Simulink for any sort of hybrid simulation, for example, or any sort of real-time sort of demonstrations. One thing that I also like, you have this very large user community that's both for Matlab and Python, but there's a big difference between Matlab and Python in that Python has a very large developer community. So there's actually people coming in and making their own code and really providing those third-party libraries. And so if you were to count all these numbers up, and I'm just having this blink back and forth, what you might have is like a 6 for Matlab, and for Python, you're verging on, say, a count of 11. And so I think that the benefits with Python far outweigh the downsides, and it's something that we should be thinking about when teaching our students. So that leads me to this third sort of aspect. So Python, which I haven't really gone through like the Python in any sort of in-depth way, but there's actually also something called a Jupyter Notebook, and Jupyter Notebook is a very interactive place where students can write their code and actually run it in real time, and embedded within that code they can actually see outputs of their scripts, and I'll do a demonstration of that in a second. And so with Jupyter, you can have live code. They can actually write equations that look like equations that don't look like code. They can do visualizations. They can comment their code with narrative text. And it supports over 40 programming languages. So if they don't like Python, they could use R. They could use other big data tools like PyTorch and TensorFlow, which are becoming more and more popular in the machine learning community. And it allows them to really interact with their code and interact with anybody who is reading their code through this sort of self-documentation. And I'll explain that in just a second. And what we've been using these Jupyter Notebooks for is for live demos, for homework sets, for projects. We've embedded it as HTML right into our course web pages, images, videos, you name it. So it's a quite nice and user-friendly tool that sort of supplements the Python programming. So I like Jupyter and Python because I think what we're really trying to get for our students is some sort of future research and industry use. And so if we're leveraging this highly community-supported programming language along with the sort of documentation through the Jupyter Notebook, I think we can actually do something that's quite powerful. And so this leads me to this last part, which is so we have Jupyter and these Jupyter Notebooks, and we have sort of this Python programming language. And then we also have this DesignSafe community, and you can actually access both the Jupyter Notebooks and Python directly through the DesignSafe portal. And so you can get access to OpenSees or the new OpenSees version, OpenSeesPy, which uses the Python version of OpenSees, which can be directly accessed through the Jupyter Notebooks. There's a number of online tutorials that are available on DesignSafe on how to use these tools. And the part that I like the most is if you have your students use the Python and Jupyter sort of applications on DesignSafe, it requires them to actually register on DesignSafe. That means that they're actually receiving every single email that you receive about the natural hazards community. And so it's a great introduction to many students to the multi-hazard research community. It gets them involved in research, if only through email spam. But I've received a number of emails after students have registered, and they're seeing, there's, for example, a blind prediction contest that was emailed out a few days ago, and I got an email saying, was this blind prediction contest similar to what you talked about in class when you talked about numerical methods? And I said, yes. And so it's great that we're able to get these students in early by sort of making them register within the DesignSafe community. And the thing that I think is very important is that there's no installation required. If you use Python and Jupyter Notebooks through DesignSafe, you do not have to install Anaconda. You do not have to use any sort of pip installation method. It is already right there. It's accessible everywhere. And it's easy, so they can just go right into programming without trying to install something on their computer. And finally, because it's accessible everywhere, we can use it for real-time classroom demonstrations. So I can log into DesignSafe, put my code up, and just program right in front of the students without being on a computer that necessarily has Python or Anaconda or anything else like that installed. So it makes it very accessible to teach in the classroom, as well as have your students use Jupyter Notebooks and Python. And so now I think it's time for a demonstration, because I feel like I've been sort of talking a lot. And so what you could do is just have your students create an account. They create an account on DesignSafe, they log on to DesignSafe, and then they get immediate access to the Jupyter portal. And so I actually embed HTML programming code directly into our Canvas webpage. We use Canvas. And I hope that everybody can still see my screen as I sort of flip between things. So let's see, hopefully this works. And so I think a lot of schools are moving to sort of a Canvas interface for their classes. So I teach structural dynamics, so here's my Canvas webpage. So I've embedded my syllabus, for example. And what's really cool about this is that I've embedded HTML of a Python script directly into this Canvas page. And so I can click Set up Python Notebook, for example, and it will download an HTML file that basically says, okay, here's actually a Python script that shows you how to set up a Jupyter notebook, and so they can go through the installation process. They can register an account on DesignSafe, and it walks them through step by step, and it's embedded directly into the campus webpage. And so this is quite nice. So now let me switch screens back again. So hopefully this doesn't get too annoying. And so you're able to do these sort of real-time demonstrations because you can go directly into DesignSafe, and you can pull up your Python notebook, and then you can just start typing in class live, which I think makes many of us nervous. But so if I switch back to that original screen, let's see, I've sort of pulled up DesignSafe, and I can just go to Research Workbench, Workspace, and my internet's a little bit slow because I'm at home. And there'll be another number of apps that are available, and you could just go right into Jupyter and launch it. And I've actually already launched it on this next tab. And I have basically scripts for steel design, structural dynamics, matrix structural analysis, nonlinear structural analysis that are all sort of available via the DesignSafe website. So if I, for example, want to look into structural analysis, I can see all the homework for that class, any in-class demonstrations that I've done, et cetera, et cetera. So what's nice about these Jupyter notebooks, just to give you an idea, this is not my personal Jupyter notebook, but this was one by Minji Zhu, who taught matrix analysis last year, is that you can actually embed text directly inside this Jupyter notebook. And so it makes commenting particularly easy. So for example, this is a lecture that he gave, lecture 2 last year, that goes through just sort of how to program in Python, some of the basics programming language. It sort of shows that Matlab versus Python pros and cons sort of table that I've already shown. You can plug in some sort of link to any websites that you want, and I can just add under Python Basics some sort of module. I can create that as a markdown. I can create it as some sort of header. So for this webinar, for example, and it immediately pops up as something that looks really nice. I can then even create that markdown, say something even more like, I'm going to do some demo code, and that'll immediately pop up. And so what I like about this is that you can comment it in a very nice and easy to understand way. Your students can print this off as a PDF, and if we want, we can actually embed equations, which I'll go over in a second. But beyond just the niceness, like, yes, it looks pretty, but what's actually going on here? So for example, I could create a variable called, I don't actually want to call it sum. What do I want to call it? I don't know what to call it. Let's call it, this is a variable, and maybe that variable equals 1 plus 1, or 1 plus 2. And so what I can do directly into this Jupyter module, I can just print that variable equals 3, and your student is able to get real-time feedback as they're typing their code, because the output is actually being displayed directly within the Jupyter notebook. So I'm using Python programming, but the Jupyter notebook allows you to display your code quite instantly. If I want to do a loop, which is the bane of every student's existence, so maybe I want to go from a J that goes J through 3, and so I can say, let's set up this for loop that's for J in a range of 3, and I can just print J, And immediately it'll go, okay, we'll start 0, 1, 2, because Python indexing starts at 0. A little bit it takes a little bit getting used to if you're coming from Matlab. And then of course you could comment this to make this look even nicer. And so you could say, let's call that an iteration, and now it's going to call it iteration 0, 1, 2. And again, this is all real-time feedback that the student has seen. So it's quite wonderful in that respect. So let's move back to the presentation. So I think the question is, yeah, this looks nice, but how do we sort of embed this in our classroom? Because we're not computer scientists, our students are computer scientists. How do we still teach them what they need to learn, but also introduce them to this rather fabulous tool that is the Jupyter Notebook and Python programming language? And so let's move this back to the PowerPoint slides. Okay. And hopefully you guys are all seeing that it's moving back and forth and I'm not just like aimlessly talking to myself. So real-time demonstrations makes it very easy. So let's do some examples. What are we actually doing at Oregon State when it comes to using these Jupyter notebooks and Python? And I want to throw this slide not because I want to talk about Oregon State being like #3 in the nation, but because I don't actually know what this means. So we have an eCampus program at Oregon State. Apparently it's good. I really have no idea. I've never taken an eCampus class. I've never taught an eCampus class, but I think it's a testament to the fact that how we teach and how our students learn is changing quite dramatically. So for example, in an eCampus classroom, your students aren't physically present in the lecture with you. They do not have direct access to you. You're communicating over office hours that are online. It supports a number of non-traditional students who are maybe working and not able to be directly on campus. And how we reach them and how we teach those students the things that we need to know is just different. That's on top of the fact that our students are changing quite dramatically. And this is a philosophy of mine. Let's see, I became an undergrad about 11 or 12 years ago. And at the time, I think the iPhone was just coming out. A lot of the students that we have now are embedded in social media, and they use the technology associated with that in a quite different way that I think many of their professors were brought up with. And it's not that that's a bad thing, it just means that things are changing and there are many things that we could be leveraging in our classroom and taking advantage of that maybe we're just not quite using yet. And one of those, I think, is this Jupyter Notebook resource, and I'll go into a couple of the other resources as well as we go throughout this lecture. So this isn't so much about Oregon State, this is just sort of a comment that as we have this growing online educational community, how we teach our students is just going to change. And that's because now they have so much more access just to the entire web, Wikipedia, et cetera, et cetera. And so how we deal with that is just something that we need to consider. So with this Python and sort of Jupyter Notebooks and DesignSafe, we've been using it quite extensively in 3 of our classes. One of the ones that I teach, so I teach structural dynamics, so this is my second year teaching this class using Python and Jupyter Notebooks. Another class is matrix structural analysis, which is this year actually being taught as an online course. And then finally, nonlinear structural analysis, which is also an online course. So we're using them quite extensively in our online eCampus courses at Oregon State. And I'm going to mainly talk about structural dynamics because that is the class that I teach. And one of the two approaches that I really wanted to emphasize in that teaching was, can our students gain greater intuition about the mathematics? So it's a very mathematically heavy course. We're using a lot of math with sort of language that a lot of students haven't seen in quite a long time, particularly when you're getting graduate students that are coming from all different experiences and backgrounds. Some of them have not programmed before. Some of them have programmed quite extensively. The last time they've taken linear algebra and ordinary differential equations was probably their freshman year in college. And considering that structural dynamics is based off of a second order ordinary differential equation, it's incredibly important that the students have a reminder about the mathematics and what that mathematics actually physically means when you're going to the dynamics of your structural system. So can the students gain greater intuition via Python and Jupyter Notebooks about what the math is actually saying? And this is another big one, can our students effectively communicate and describe their knowledge of dynamics? So what I've found is that, yes, a student may be able to get to the right answer, but there might be some nuances as far as understanding that are missing. And so if the student can come back to me and actually explain and describe what they think is actually going on with the structural dynamics of the system, they learn something by sort of formulating a solution in terms of words or writing, or just in terms of commenting their code. And then I also learn what the gaps are. So are there things that I'm missing as a teacher that they're not quite understanding? Are there definitions that I wasn't clear enough? Is there anything being misinterpreted in my classroom? And so if the students can effectively communicate to me and describe their knowledge of what they think is happening in structural dynamics, then it's a benefit to both the student and to me, because I get to fill in the gaps. And they also get to practice, say, writing, for example, or commenting their code, for another example. So let's just sort of look at what that looks like. So because a lot of our students are coming in and they might not necessarily have programming experience, one of the easiest ways to start them with programming is to just give them a basic plotting assignment. So here's an example in a structural dynamics class. Take this Python, import various plotting libraries, whatever you would like, into your Jupyter notebooks. You can embed headings to make it look really nice. And then finally, you can embed LaTeX equations so that the equations that the students are writing actually look like equations, not necessarily like Python sort of code. And then plot it. And plot it in a way that makes sense within a structural dynamics context. So yes, they're learning how to plot in Python, but more than that, they're plotting underdamped, critically damped, and overdamped cases from structural dynamics. And so to kind of look at what that looks like, I'm gonna go back to my screen. That is not the correct screen. And let's go to what that might look like in terms of a Python programming. So yes, they're learning Python programming, but it's embedded within the context of structural dynamics. And so they can import their code, they can comment it. For example, this is the problem statement. They can import some sort of time array of zeros, and then they can print the size of that time array. They can fill that time array with some sort of variables. They can check to make sure it's right. They can create a function, they can call that function, and finally, this is just a simple plot that's sort of plotting different calls of that function, and it's plotting a sine curve. And so I don't give my students any code, they're writing this all from scratch, but they're calling a function and they're plotting a sine curve, which is one of the main sort of functions that we use in structural dynamics. And so if they see a sine curve here, they can then go to the next assignment, which is sort of that damping case, and they can look at different levels of damping. They can initialize their code. And what I really like about it is that they can sort of embed these equations. So for the overdamped case, if I were to look at that, that sort of one line of code is written in LaTeX. I've specified as a markdown, but when I run it, it looks like an actual equation that the student might see. And so they can do that for underdamped, critically damped, and overdamped cases, and then they could basically run that through a solution and plot it. And again, all of this is sort of in real time. So it can be really powerful to students because they can debug, and the way they debug is by watching and manipulating their code and seeing the output directly within that code. So it's rather nice with that respect. And so let's move back to the presentation, which I know is rather. So once you get them plotting, you can start adding layers. And so one of the things I always tell my students is that the reason that they need a program for my course is because a lot of structural dynamics relies on numerical solutions. And so we go through, for example, central difference. They type out their initial conditions, they loop over the time step themselves, and they write sort of a central difference method in these Jupyter notebooks. They load in some sort of forcing function, and then they compare that forcing function, the results of that forcing function to the output, the response from that forcing function to the exact response. And that way they get to validate their own code because they know what the exact result is. and they're able to compare it to their numerical solution. And so you can see that we can add layers. So we started with plotting, now we're moving to central difference, and they're actually plotting it all themselves. We then go over NUMark, so they can modify central difference a step further and implement NUMark's method all within this Jupyter Notebook interface, and they can start creating sort of functions that sort of describe those methodologies. And again, just sort of labeling things as constants, initial conditions, and again, they can loop over the steps. And so they started out with just plotting, but now they're talking about for loops, and then we've added another layer which says, well, let's make the NUMark method a function that you can then call. And again, let's compare all of our responses to the exact solution. If you have, for example, a solution that happens to have a analytical closed form solution. And then you can add one more layer to that and basically loop everything like central difference method, for example, or NUMark within some sort of looping algorithm that loops over a period. And so now they can go one step further and start looking at response spectrums and creating their own response spectrums, basically calling their central difference or NUMark function. And then they can take another step further again and say, well, let's actually implement nonlinear response into our system and see how the response changes when we have some sort of nonlinear material parameter. So everything is incremented very slowly. Each homework assignment builds off the previous homework assignment. And so if they're following along, they actually pick it up fairly fast and they're able to go from basic plotting to something like nonlinear dynamic analysis. Granted, it's a lasto perfectly plastic material behavior, but it's nice. And so they're also able to comment directly within the code. And so anytime, they're commenting their code, but they can also comment on the behavior that they're seeing directly into the Jupyter Notebook. And so it's not just putting in headers or describing what they're doing, it's also commenting on what they're seeing. And so if I go back to the Jupyter Notebook screen and look at central difference, for example, I like this example because I think it's like their first step beyond plotting. And so they can sort of create a header, they can load in their properties, they can load in some sort of function representing the forcing function, and they can loop it and directly output whatever that loop is doing. So right now it's basically filling an array with a forcing function at index j. And then if they want to look at what that thing that they just put in to the Jupyter Notebook looks like, they can plot it directly, and that's before I've run the entire script. So they can check to see whether it looks that inputted forcing function looks correct. They can then initialize some arrays and loop over the time steps with the central difference method. They can compute the exact response, and then finally they can plot the exact response over their approximated loading. And what's really cool about this is right now I'm using a time step of 0.1 seconds. I can make that a time step of 0.01 second. And let me just run this. And I can restart and run everything with this new time step. And they can see it basically update. And now we see that the approximate solution using central difference approaches the exact loading condition. At the same time, central difference has some issues with stability, so I can go back up here to the time increment, and I can basically make this thing go unstable. And again, the student will see that output directly. Now we can see that the solution algorithm is becoming unstable, and it's basically the error is unbounded, and we're seeing that error grow. So again, all of these can be fairly powerful tools for our students. So if I go back to the PowerPoint, I seem to have lost my mouse. Let's see. So they get quite detailed. And one thing that we can also talk about is that you can actually create your lecture notes and your lecture and tie them together. And so, for example, you can have a lecture note that sort of calls the markdown feature in Jupyter Notebook that sort of has all the lecture characteristics. For example, this is for matrix analysis. And then within that lecture, you can embed live code and actually type in your live code in the lecture. So they have both the lecture notes and a live code demonstration all in one. And so you can, for example, input images so that they could see sort of structure they're looking at. And then this is just an example of basically all in that Jupyter notebook. You have this image, you have these lecture notes, and then you actually have the code that's also embedded within the Jupyter notebook. And all of this prints as a PDF. So it's very nice. You can also do something even a little bit more extravagant. So we can look at nonlinear structural analysis, and you can have the students create a force, a basic force, basic stiffness sort of function, and you can actually have them implement maybe, this is Newton-Raphson iterations. And so they're able to actually output the convergence and how many iterations it takes for each time step to converge. And so that's one of the sort of programming homework assignments that our students do in nonlinear structural analysis. So there's a lot of different things that you can do, and the sophistication becomes as sophisticated as you want as a teacher. And finally, they can look at that convergence in terms of a load versus displacement plot after running the Newton-Raphson iterations. So one of the great things about moving to Python is that OpenSees, which is a very common software for structural analysis, is now available, and just earthquake engineering in general, not just structural analysis, is now available on DesignSafe, and also with, you can actually call it in Python. So if we can go back to the sort of demonstration, and I know I'm showing quite a bit of things here. Let's see. So this is actually some research one of my students is doing with me. And what you can do is call OpenSees as one of those libraries that you load in. So you can almost think of OpenSees as being one of those third-party libraries. You can run some code. You can have it read some sort of AISC shape database. It's going to read a ground motion record. And then it's basically going to go through and it'll tell you basically what it's running. And it'll plot whatever system that you're showing, and it'll show the periods. It ran the gravity analysis. It's putting some recorders into an output file, and it's running a nonlinear dynamic analysis. And all of these things are being embedded within the OpenSees script. So it's quite nice because you're not having to move from Tickle or to some pre or post processor. You have OpenSees and Python all embedded into one thing. So that's pretty nice, and we actually introduced that in our classroom in nonlinear dynamic analysis, nonlinear structural analysis, and so they do quite a few homework assignments in OpenSees using the Python language in that class. So that's sort of Python and Jupyter notebooks. Let's go back to this guy. And so there's a lot of things that you can do there, and I would say that the way we're approaching it is rather iterative. We're trying everything, and we're sort of refining it every year. But one of the things that I like to point out is that there's also a number of educational apps that are available on DesignSafe through the SimCenter as well. So everything that I've basically just showed you is static. So yes, your students are getting real-time sort of outputs from their code. They're able to plot within the code, in line with whatever code they are using Jupyter notebooks, but that doesn't necessarily mean that in a dynamics class they understand that those plots are actually representing something that is moving. And so one of the big questions that I have is, how do you bring structural dynamics into a dynamics class? And so there is a SimCenter tool called the MDOF tool. It's available on DesignSafe. And it allows you to change real-time inputs. For example, right now, we're changing the yield strength of one of the stories, and you're able to actually see an inelastic, this MDOF system behave inelastically and see the results of your inputs to what happens to dynamic response in real time. So it's real-time visualization of the inputs and how those affect linear or nonlinear dynamic response. And then it begs the question of, so you have this tool, how do you actually use it in your classroom? And so one of the two prongs that I sort of introduced at the beginning of this lecture is that I'm interested in having the students sort of decipher the math, but I'm also very interested in having our students communicate their ideas and how much they really understand what's happening in the lectures, their homework, and in the classroom in general. And so what I do is I give them this tool, and I just say, hey, play around with it. I'll give you some ideas for inputs. But then what I want you to do is I want you to just to, like, in some way, using equations, figures, or text, totally open-ended, describe that motion and tell me what you think this system is doing. And it's very interesting. So I've added a couple things since I initially started this. The first thing I added was this question requires a short 1-paragraph answer. The other thing that I added was this question is intentionally open-ended. Because having something where it was like, do whatever you want, explain this in any way that you feel is appropriate, was just, it was, the students didn't really know what to do. So I've started refining this question a little bit, but I still like the idea that it's extremely open-ended, and they're able to communicate with me through writing any sort of behavior or mechanism in this MDOF app that they're seeing. And they can use equations to do that, they can use figures to do that, they can use writing to do that, but I want them to explain to me how they actually think this dynamic motion is occurring and why. And so there's sort of a setup that goes along with this as well. So most of the students coming into my structural dynamics course, they're coming either from right out of undergraduate. It's like one of the first courses they take as a master's student. So they're coming right out of their undergraduate education, or they're coming back from industry. And so what I do is I give them the app and I say, okay, look at this movement. We'll look at it SDOF. And just kind of explain to me, you know, based on your undergraduate knowledge, what you think is happening. I mean, this is lecture 0. Like, it's the very first lecture of the course. They haven't really seen anything. They haven't seen the math. They haven't seen anything related to structural dynamics as far as it being a master's level course. And again, it's very open-ended, and it's the exact same sort of setup. Use equations, figures, or text, and let me know just kind of what you're thinking about this MDOF tool. And so they'll get something that looks like this, where you have this SDOF that's oscillating back and forth, and they can plot it in terms of a force displacement history, and it looks like some sort of sine or cosine function. And they basically tell me what they know based off of their previous knowledge. And so they're able to communicate to me where exactly they are upon entering the master's program. And then after a week, we've had a couple lectures on, let's say, free vibration response. And so I come back and I'm like, okay, hey, back on what you stated on homework 1, that initial homework assignment with using the MDOF tool, can you recall your answer? And then tell me, based on what you've learned in class, did your answer somehow differ? And some students say, oh, no, I already knew everything the first time. But it also allows them to sort of like recall a previous homework assignment, reformulate their solution in terms of the new material that's hopefully new that they learned during lecture, and help them sort of give feedback to themselves. So you wrote this thing during week 0, how did your answer and how did your learning change on the following week? How much have you gained actually in the classroom? And it also allows me to sort of assess that week 1, where the students are, how much they're learning in my class, based on their previous experience and previous knowledge. And then finally, you can do that for any sort of motion. So that was free vibration. So you can have the MDOF tool, for example, include harmonic motion. And so they again go back to the tool and they comment the response for different ratios of input frequency to the natural frequency of your building. And again, they comment the difference response. And you can see that with harmonic inputs, the response somewhat changes. And when you look at the forward displacement history, you can see that it's sort of a steady state response, and then superimposed on that is sort of a free vibration or transient response. But that's not something that they would necessarily, that's something that's easily seen if you look at the plot, but maybe less obvious when you look at the actual displacement of this SDOF system. So it's really able to make dynamics come alive. They're actually able to see this thing moving in real time. And so they can do that same exact thing for a pulse motion, and they can look at a short pulse or a long pulse. And then finally, when we get to the numerical analysis, this sort of MDOF tool is actually directly coupled to their Python and Jupyter notebook programming assignments. And it basically says, okay, you've been programming Newmark's method, central difference method for linear and nonlinear systems. Now, what do you think is actually going on in the MDOF tool? Like if you were to actually crack open the source code and look at it, what do you think it's actually doing? What sort of assumptions is it making? Peeking into the black box. So they're able to actually see this sort of thing that's moving, and then also sort of think about the engine that this GUI, this user interface is sitting on. And so then they can start getting into something that's rather complex. That's something that may be very difficult to visualize. So for example, with an MDOF system, and then including some sort of inelastic nonlinear response. And so one of the other tools that we use is, and I'm kind of biased because this is a tool that I wrote and created, but it's I do a lot of research in brace frames. And so what it does is it takes a brace and you input some sort of inputs, numerical inputs, and it basically plots an experimental result with whatever results are coming out of your numerical analysis. And it plots the moment diagram, axial force diagram, display shape, and you can sort of change, again, in real time, you change your user inputs and you can sort of compare it to that experiment result right away. And so I kind of like to call it peeking into the black box, because now the student is starting to look at not only the results, but they're also looking at how do my numerical inputs affect my results, and how does that compare to like the bench response or this this response from this experimental test. And I'm pretty proud of this because I've actually had an undergraduate research student extending this app. So he's an undergraduate level, and so he's actually coding in C++ and revising this sort of app to include curvature response as well. And so not only is it introducing C++ programming and numerical analysis at the undergraduate level, I can also just basically take this thing, use it in my research, and students understand right away how do number of integration points affect my response? How does how my integration method, how does that affect my response? So on and so forth. So it's quite an easy peek into the black box. And so just in summary of the things that we've been doing at OSU when it comes to sort of using DesignSafe and leveraging the Python and Jupyter notebook applications that are available there, and the SimCenter educational tools that are also available there. We've embedded our Jupyter notebooks directly into the course webpage. We can embed them in HTML. It allows our students just direct access through the course webpage to these Jupyter notebook assignments, which are easily commented with headers and very descriptive and so on and so forth. We all use Jupyter notebooks differently at OSU. So I particularly like it for in-class demos, but if we looked at sort of what we've been doing with matrix analysis and nonlinear analysis, we've also created Jupyter-based lecture notes, example scripts, and all of those can be done very easily using the Jupyter notebook and Python scripting language. So all of our homeworks, we've gone completely to Python at this point. We're not using any Matlab. So we can have them turn them in as PDFs, or we can have them turn in their IPython notebook and have them actually be checked automatically. I don't have that set up, but I know that that's what's done in matrix analysis and nonlinear analysis. We do a final project with Python and Jupyter. All three of our classes leverage both those tools for a final project, and we don't really give them any code. We just say, hey, you know, based on what you've learned throughout the course, try to develop a code for this problem in a way that makes sense to you. And finally, we've been heftily taking advantage of the fact that OpenSees is now available in Python, and so we can use it in our classroom, and we can also use that in future research applications. So it's just, if you introduce the students to Python and Jupyter notebooks early, they can just also leverage OpenSees directly within that framework. And finally, we've been, or at least I've been, using the SimCenter tool, primarily the MDOF tool, to bring dynamics into the classroom. It's a very easy to use app. They really don't need much effort to be able to use it. It gives them some intuition about the behavior behind the equations. And if you give them an open-ended enough sort of assignment, then it allows them sort of to critically think and discuss the behavior that they're seeing. And finally, it's a nice way if you want to create your own app to engage undergraduate students in research and programming early. I know it seems like a lot to give an undergraduate student, like here, take C++ and just program. You'd be surprised what they can do, and the applications that come out of it, or at least in this case, was very successful. And I truly believe introducing programming and sort of numerical methods early in the undergraduate student career it can only be a good thing. And so I just kind of wanted to end with my opinion, lessons I've learned, and potential iterations. So this is very much still iterative. I'm still learning about how to use Jupyter notebooks and Python in the classroom, about how to successfully leverage these applications, how to successfully set up sort of open-ended homework questions without giving too much away and having the students sort of think about how they want to answer. And all of this is an opinion, but I'm just going to say a couple things. Programming takes a lot of practice, and a lot of students coming in don't have any programming experience even at the graduate level. You need to give them enough time to sort of think about how the programming language works, how for loops work, how functions work. And so that's why I like to introduce Python very slowly. And so I typically introduce Python via plotting, and then eventually we'll move to loops and eventually functions. And so you implement it in a very gradual way. And so they're not seeing loops and functions right off the bat, but they're doing something that's fairly simple at first, but then each homework assignment builds on the next homework assignment. I also like to keep every single assignment that I have relevant to the class material. So I don't teach programming. I am not a programmer. I am not a computer scientist. At the end of the day, I teach structural dynamics. So I believe that programming is a tool. And to successfully successfully leverage that tool, I think that each of my assignments need to have some sort of programming associated with it. But I still want it to keep the structural dynamics sort of concepts embedded in it. So I do believe that we need to teach more programming, but I think it needs to be within the context of the problems that we're dealing with. I also think critical thinking takes practice. So when I first started introducing the sort of open-ended questions, which was like, here's a question, just describe to me what you see. I found that students didn't really know what to do, because a lot of them are coming from an undergraduate education where they've been given a lot of steps. And so they were used to following steps and used to taking directions. So having something that was completely open-ended, they kept on thinking that they were doing something wrong or that they didn't understand the problem statement. And to me, it just takes practice. So what I've seen is in these open-ended written assignments that are basically say, hey, take this M.dot tool, tell me what you see, describe what you see. If they do it enough times, they get pretty good at it. So what you see at the beginning of the class is that they have an assignment and they don't really know what to do with this sort of very open-ended question. And then they start sort of formulating more and more precise answers to the question every homework assignment. I highly recommend, if you are going to leverage Python or Jupyter notebooks in your classroom, give your students as little opportunity to copy and paste code as possible. If they are forming their own code and writing their own code from scratch without you giving them anything, they're actually more likely to really understand what that code is doing. For the novice programmer, looking at someone else's code is extremely difficult and very difficult to understand what that code is actually doing. But if they do it themselves, if they practice it themselves, I've found that they're more likely to actually understand what that script, whether it's Newmark's method or central difference method, is actually doing within this for loop. And then finally, if you're not going to give them any copy and paste code, let them at least have some sort of final project to formulate a solution that makes sense to them in the way that it makes sense to them. So I know it's more difficult to grade in this way, but if we let the students sort of formulate their own solution in a manner that makes sense to them, then the actual problem might also make more sense to them, rather than having it like in this sort of template form, which might be easy to grade, but might not give the students as much experience sort of dealing with all the different sort of variations that can come with programming. So I can program Newmark's method in probably 10,000 different ways. And so having the students sort of come up with their own way, I think, is important to the learning process. So finally, if programming takes practice and critical thinking takes practice, then writing definitely takes practice. And so having those open-ended writing assignments, every single homework, actually, I think was extremely helpful. Not only to the student, because they're able to sort of write down what they think they know, but it was really important to me, because I could read their written assignment and I could immediately see the gaps in my own teaching. Because if they couldn't describe something to me, or if they misinterpreted something that I said, I could see it directly into that problem statement. And so this is just sort of, again, an opinion, but take advantage of whatever feedback that you can, whether that be real-time feedback using Jupyter Notebooks or the MDOF tool, or through written assignments. But if you give them enough different ways to learn, and enough different ways of seeing the problem, I think you'll be relatively surprised on how creative they end up becoming. And so just to say that there's plenty of documentation on how to use Jupyter Notebooks and Python. And I strongly urge everyone to at least give it somewhat of a chance. The Jupyter Notebooks make programming, at least looking at assignments, much easier. It makes debugging for the students much easier. And like I said, they're able to comment their code directly within the notebook framework. So, and with that, I will wrap up. And I think that's, Charlie, is that when questions sort of start happening, or is anybody even still there?
Actually, everybody's still here.
Oh, fantastic.
So, thank you so much. If anyone has any questions for Barbara, please go ahead and type that into the chat and we can discuss it. But no questions come up yet or during your talk.
Okay, that means I talk too fast.
No, there's a lot to digest. So, how many courses do you teach?
So last year I taught 2. So I did undergraduate steel design and then structural dynamics at the master's level. This year I'll be teaching 3. So we're on a quarter system, which also makes things fairly interesting. So we only have 10 weeks to teach a lot of this material.
Oh, wow.
So everything is condensed. And fitting in as many things as possible on top of the programming can be very difficult. So having some sort of structured framework where each homework assignment builds upon the next is absolutely critical. And if you have a student who decides not to do homework 3, then they're most likely not going to know how to do homework 5 through 7, for example. So it's definitely a complication. But anyway, 3 in the quarter system starting this year.
So I do have a couple of questions. First off, Chinyin Lu, yes, we will make these Jupyter Notebooks and the presentation, or I'm sorry, I'm answering the wrong question here. Within Kirkham, yeah, we will have the PowerPoint posted to our DesignSafe archive. Actually, Barbara, if you want to stop sharing, I'll go and share my screen where.
Yeah. Do I just hit? Okay.
Yeah,
I think I did.
there you go.
Okay. Great.
All right, so in answer to some of these questions, first off, the DesignSafe Learning Archive, so if you go to the Learning Center and then click on Training and Education and Training, you'll have a current calendar of all the events that are coming up. And if you scroll down a bit farther, you will have all of the tutorials and webinars we've done with the documentation that goes with it, linked as well. You'll also be able to find all of our webinars on YouTube, on our DesignSafe YouTube channel as well. And finally, I knew there was another question here. Let me bring up the chat again. And also, Barb, there's a question for you, because does the embedded Jupyter Notebook and DesignSafe run on the cloud computing engine? Actually, I think I should take that one. Yes, it does. So the way DesignSafe is, the way the DesignSafe is created is we have a cloud resource available behind the scenes. Some of it is sitting on our supercomputer Stampede 2. Some of it is sitting on some of our cloud-based resources. And what happens is when you log in on a Jupyter Notebook is you are firing up a VM and sitting in a container that is actually given to you. And then all of your documents and your notebooks are mapped from your data depot to that virtual machine.
I guess
can
I add something to that?
Yeah.
So the ones that I showed with the OpenSeesPy Python, that was like sort of a research-driven thing. We were running those on DesignSafe, but what I actually showed you was on my local machine. If you're doing like a hefty amount of data lifting, I don't know that. And maybe Charlie, you have a little bit more information on the best way to do sort of like if there's a lot, if it's like more than just an assignment. I've been tending to do it on my local machine. Like if it's more of a research-driven application, or running it over TAC or something like that. And so I don't know if you have a comment on that side of things. Like if
I've noticed as soon as I can get the data into DesignSafe, I usually have not had a problem with hitting limitations.
Okay.
But and then all the stuff that I've done, I've started with like an empty sheet, so I was able to just create the data on the fly. I've never had to actually import anything in specifically for my stuff. But if you do use Globus, then Globus is really the best way of getting large data files into DesignSafe. But like I said, there's a lot of tweaking and a lot of setup to get Globus working properly.
Okay.
But yeah, most of the time, I just honestly leave my data on DesignSafe, and I don't, that's the only place I ever deal with it.
Yeah.
And most of the, like I said, almost all of the Jupyter notebooks run in a VM that is spun up specifically for you, so nobody shares any resources. And then all the data, some of the OpenSea stuff that you do, those are actually ran on a variety of machines depending on which OpenSeas you're looking at and how much machine you need to crunch through the data. Let's see, there's a couple other questions. Someone was wondering, do you know of any alternative for Simulink that works with Python?
Oh,
Simulink?
I don't. That's a pretty hefty downer to Python, actually. Yeah, I don't. Simulink, that's just one of those things that it's developed over Matlab. I don't know. I'm sure someone will do it something like that eventually. I haven't really heard of anything. So not that I know of. That doesn't mean that there's not something out there, though.
And also from Yvonne Marino, she'd like to know if your students have already taken a structural analysis course before one of the dynamics.
So dynamics is a master's level course that doesn't. So yeah, most students are coming in with an undergraduate degree, but I get a lot of students that are also not structural engineers. So for example, this year I have a couple of mechanical engineering students, and then I have a couple students that are doing fluid structure interaction for offshore wave energy. And so so I try to make structural analysis like not as needed, which is always difficult because it's a structural dynamics course. So I tend to focus more on the dynamics, and then the structural analysis is rather simple structures. So as of now, no, they do not need a prerequisite in structural analysis. But hopefully they've taken a couple courses.
All right. If there are any other questions, feel free to ask them. While at that, I'd like to take the time to thank you again, Barbara, for joining us today and running the webinars. I really enjoy having the DesignSafe community actually presenting the webinars because it gives you a different take on how the technology is being used by the different communities and that DesignSafe serves. It's actually really cool to see. So thank you so much for your time. We hope to be doing more of these. Hey, also want to let the audience know that come November, there are actually 2 DesignSafe webinars on the schedule. They haven't made it into the links yet. They haven't been, but to keep an eye out for those. Also, if you have any questions, feel free to find us on Slack. You can ask the questions there and the general questions, or you can find one of us directly as well. There's also a training channel on DesignSafe Slack as well. You can also email us at training@designsafe-ci.org or fill out a help ticket. If you have any, once again, thanks so much for joining us today. If you guys have any additional questions, feel free to take it to one of the other resources we have. And with that, once again, Barbara, thank you so much for joining us today and running the show. It was awesome having you. And hopefully we'll have you again in a coming webinar as well.
Okay, thank you. So am I good? Am I good to go?
I think you're good. I'm going to go ahead.
Oh, okay. Fantastic. Awesome. Okay. Thank you, everyone. I have to figure out how to leave the meeting. Oh, there we go.